Hey everyone, welcome to KSSP Podcast. I'm Spencer.
And I'm Katie.
And today we're going to be talking about stars and their life cycles. So, with this series today, we're just going to talk about stars, what they are, and then the different stages in their life cycle. So, we'll start with a star is any massive self-luminous celestial body of gas that shines by radiation derived from its internal energy sources.
And we will be going over the life cycle of a star. So stellar nebulas, the differences between different sized stars, planetary supernovas, neutron stars, and black holes. So we can start with this video, GCSE Physics, the lifestyles of stars, how they're formed, and some other stuff.
Yes, so we'll get started.
In today's video, we're going to look at the life cycle of stars. It all starts with a big cloud of dust and gas, which we call a nebula. Over time, the attractive force of gravity pulls the dust and gas together to form a structure called a protostar. And as more and more particles collide and join the protostar, it gets bigger and bigger. And so its force of gravity gets even stronger, which allows it to attract ever more dust and gas. The gravity also squeezes the protostar itself, making it more and more dense. This means that the particles inside it collide with each other more often, which in turn raises the temperature of the protostar. Then, when the temperature and pressure get high enough, hydrogen nuclei start to fuse together to form helium nuclei, in a process called nuclear fusion. This gives out huge amounts of energy, which keeps the core of the star hot. And it's at this point that we call it an actual star, or more precisely, a main sequence star.
So, gravity. Again.
Oh yeah, it always comes down to gravity. If you're ever dealing with matter that has mass, why? Because that's just the way it goes. That's just the way the universe is coded.
Because it's the objects that have the gravity.
Right.
So the gas and dust has gravity.
Yes.
And then the gravity of each other is pulling it together.
Yeah, it's like, it sounds like it's squishing it at the center, making the particles collide.
And what keeps that from happening to us in a planet, Earth, the star? Like, why don't we get pulled together?
More stable elements, like carbon.
Oh. Okay. I mean, I guess I get...
That would be my guess, at least. I mean, I'm not a scientist, but...
So, like, the universe starts as gas and dust and then forms stars and planetary bodies that then have mass and gravity enough to where it's the exact amount needed to keep each other at the safe distance?
What do you mean by that, I guess?
So, like, the Earth and Sun have just the right amount of mass and gravity to keep each other from being pulled one way or the other.
Yeah, and also the distance too. Don't forget the distance. Because if we were like, I think the distance has to do with it too.
Yeah, but what created the distance? Did the Earth just magically form at that particular distance? Just we were lucky?
Probably the same way, similar way to how stars form, just from, the Big Bang and matter being expelled everywhere, making a big old mess. And then, like, eventually the gravity of all these, little particles and all these atoms, like, will come together and form different types of matter, I guess, is the best way I would explain it. I'm really terrible at explaining this, but...
Well, No, I guess like I think I get what you're saying. I don't know if it answers like my
Yeah.
but I don't know if there's an answer to my question because I don't
There
think
might
they
not be.
know.
I was saying there might not be an answer. I don't know.
Because really, how would we like? They're like, because basically my question is, why are we at the perfect distance? Why are the planets at the perfect distance? Why did they form at that particular distance?
Oh,
Just
I
luck?
assume that other matter had also formed, but because it would be like maybe an incorrect distance from the sun, let's say, like it would either get sucked in or propelled out.
So you think, okay. So in your theory, then there's been, like, if the sun is like we're just gonna say the sun is in the middle, and
Yeah.
then there maybe were tiny little forming around the sun, but then what's the first planet from the sun?
Mercury.
Mercury also was forming.
Yeah.
I guess, like, why were all these forming? Like, what prevented them from all getting pulled into the sun?
I mean, I think that's just the way that the gravity works. I don't know if there's an answer really to that question. There might be. There could be.
I mean, I guess there doesn't have to be an answer. It's just that's what I'm thinking. Like, why?
Yeah. Oh, yeah, that makes sense.
Because then it formed a perfect. I mean, maybe not perfect in some people's eyes, but just it formed a perfect, of what we consider perfect universe, because it allows us to live. You know.
Yeah.
Like, if it would have been
Maybe
any
not
different,
the
then
universe.
humans probably wouldn't exist. But
Yeah, true.
it's just interesting.
Yeah.
It's comes down to luck, I guess. Is what I think.
True.
It's just luck. But okay. Should we keep playing?
Yeah, let's keep going here.
See what else.
While it's a main sequence star, the outward pressure caused by all of that energy that's being released by nuclear fusion is perfectly balanced by the inward pressure caused by gravity. This allows for a long, stable period that can last for billions of years. And it's this stage that our sun is currently in. At some point, though, the star will start to run out of hydrogen, which, remember, is effectively its fuel. You don't need to worry about the details, but basically this means that the star won't be able to do any more nuclear fusion. And so the inward pressure of gravity takes over and contracts the star into a small ball until it's so hot and dense that nuclear fusion can start up again, which will cause it to expand again. This time, though, instead of just forming helium, the nuclear fusion will form heavier elements, including all the elements up to iron on the periodic table.
Wait, pause. Has this happened to our sun yet?
No, I don't. What do you mean?
Like this part? Like, have we gotten to the part where it condensed and then grew back, or is that still coming? Is that still coming?
Oh, I think it's still coming, isn't it? Like, if they were, because in this,
yeah, because the sun is 4.6 billion years old, and it's about halfway through its life cycle.
In our theories,
yeah,
according to theories,
yeah.
Well, because in this stage, doesn't it? Our sun still has hydrogen, though, doesn't it? Like, with the measurements they've taken.
Oh, that's true. Yeah.
And I think in this one it ran out of hydrogen. I think
it also makes heavier elements too, though.
Our sun does?
From what I was reading, yeah.
I don't know then.
Maybe it's done this. I don't know. Because I imagine, like, the inward pressure, like, if there wasn't any way, like, if it didn't keep making fusion as it got smaller, like, isn't that how, like, a black hole would form at the end of the life? Is because it's not able to make any more fusion, so it would, like, the gravity collapses on itself, basically.
Like, it's not putting any outward, exerting the fusion force.
Exactly. That would be my theory at this point, but maybe the video will prove me wrong.
We'll keep going and see what they say.
For sure.
exactly how much the star expands depends on how big the initial star was. If it was a small to medium star, like our Sun, then it will form a red giant. But if it was a really big star, then it would form a red supergiant. Each of these two types complete the rest of their life cycles in different ways. So we're going to take a look at the red giant first, and then we'll come back to the red supergiant.
Okay.
After a relatively short time, the red giant becomes unstable and expels its outer layers of dust and gas. This leaves behind a hot, dense, solid core, which doesn't do any nuclear fusion. We call this a white dwarf because it gives off lots of light, so it appears white, and is relatively small. Over time, the white dwarf gets cooler and darker as it emits all of its energy, until finally it transitions to a black dwarf because it no longer has enough energy to emit light, and so appears dark.
Interesting.
Now, if we whiz back to the two options for our main sequence star, the other possibility for the really big stars was to turn into a red supergiant. So let's now look at these. Red supergiants actually start to shine brightly again as they undergo even more nuclear fusion.
Oh, wow.
After passing through several cycles of expansion and contraction, though, they eventually explode in something called a supernova, which forms elements even heavier than iron that get ejected all across the universe. What happens next, again, depends on how big the star was. If it was just very big, then it will condense into a very dense core called a neutron star. However, if the star was absolutely massive, then it might collapse in on itself and become a black hole.
Yep.
The reason we call them black holes is because they're so dense that their gravity is able to pull in any light that passes nearby, which means that they literally appear as empty spaces or tiny holes in the universe where no light is ever emitted. So to quickly recap everything, stars initially form from clouds of dust and gas that slowly come together under the attractive force of gravity to form a protostar. When the pressure and temperature get high enough, nuclear fusion takes off, and we transition to a main sequence star. After a long time, often billions of years, the star exhausts its hydrogen supplies and becomes either a red giant, if it's a small to medium size, or a red supergiant if it's a big star. The red giants throw off their outer layers to reveal a hot, dense core that we call a white dwarf, which then cools to become a black dwarf. Meanwhile, the red supergiant explodes in a supernova, ejecting heavy elements across the universe. And it then condenses into a neutron star if it was only pretty big, or into a black hole if it was truly massive.
Pause it for a sec. So, I guess we're almost done with it, but is the supernova, is that an implosion or an explosion? I don't know if you mentioned that. If I missed that.
I think
I can look it up too.
I want to say explosion. But I don't know if he did mention that.
Oh, okay, it is an explosion.
And then for like our knowledge, everything that our knowledge on fusion that we use on Earth or attempt to use for energy sources, did we learn all that from astrology? Or did some of
Astronomy,
it
you mean?
Yeah,
I would
astronomy.
say astrology is different, yeah. But I would think so. I don't know for sure, but I would think we learned that all from learning about the sun.
Interesting. So we're just trying to copy what the sun does.
I guess. In a sense.
That's interesting. Yeah, I don't know. It's just interesting that stars are like their own reactors, you know, kind of.
Yeah.
Like they have their own internal reactors, and
Yes.
it just happened again, you know, like it just because
yeah,
the fate of the universe dictated it, you know.
Yes.
Okay.
That's everything for today, though. So if you enjoyed it, then please do give us a like and subscribe, and we'll see you again soon.
All right, cool.
Sweet.
So, all right, we're going to talk about the life cycle of a star. And I just want to show an image really quick that I think looks really pretty from this article. That's this life cycle of a star right here. So there's a stellar nebula, right? And then the average star turns into the red giant, and a red giant turns into the planetary nebula, which it looks like it contains the white dwarf. I'm not sure if that's the same thing in the middle of the planetary nebula, but we can learn.
Yeah.
And then if it's a massive star, it'll be a red supergiant, turn to a supernova, and then either a neutron star or a black hole, or both potentially. So the lifetime of a star depends very much on its size. Massive stars use up their fuel quickly. This means they only last a few 100,000 years. Smaller stars use up fuel more slowly, so they will shine for several billion years. So eventually the hydrogen which powers the nuclear reactions inside the star begin to run out, and they enter the final phase of their lifetime. So they expand, cool, and change color to become a red giant. And then what happens next depends on the size of the star. So the smaller star, like the sun, will gradually cool down and stop glowing. During these changes, it will go through the planetary nebula phase and the white dwarf phase. After many thousands of millions of years, it will stop glowing and become a black dwarf. A massive star experiences a much more energetic and violent end. It explodes as a supernova, and this scatters materials from inside the star across space. And the material can collect in nebula and form the next generation of stars. And then after the dust clears, a very dense neutron star is left behind. These spin rapidly and give off streams of radiation known as pulsars. And if the star is especially massive, when it explodes, it forms a black hole. So that's that article. And then I've also got some fun facts about stars and the life cycle of the stars and the sun. So, let's see. Every star you can see is much bigger and glows brighter than our sun. The sun looks the brightest and biggest because it's the closest star to us. You can't see 1 million stars in the sky at one time. You cannot. The color red doesn't mean hot in space. It means cool. So if you look at a red star, that means the star is cool, not hot. If the star is blue, that means it is hot. And stars have black bodies, and there are no green stars. That means not many stars look green, and if they do, it's because of your telescope. Our sun is actually a dwarf star. Stars don't actually twinkle. You can see at least 20 quadrillion miles into space. Wow. And then black holes don't suck. They just use gravity to pull stars and space junk into them. The sun is the star that provides the conditions to live on Earth. So those are some fun facts about stars. I think you had a couple more.
Yeah, I have a couple here that I found when I was looking things up. So I found that the stars in a particular cluster have a common birthday. They formed from a gas cloud all at the same time. Some stars are born having high luminosity and high temperature, while others are born having low luminosity and low temperature. And then the centers of stars, as we learned, are hot enough to create a nuclear furnace. All electrons are stripped entirely from their atoms, leaving their nuclei bare. And then just how long like a massive blue star can live for perhaps 10 million years. So it's just interesting how, like, the length of time that stars.
I just think the
live
blue
for.
stars are interesting to me.
Blue stars?
Yeah. It just sounds so pretty.
Yeah. I guess I don't know much of the difference between the different colored stars, but
Yeah, I'll go over that later too.
oh, okay. But yeah, stars are just, I think, yeah. They all have their own unique beauty, right?
They're so big. Like, you think about how big they are. Like, it's crazy. And our sun is way bigger than the Earth, and it's like not even close. It's a dwarf star, that said. It's a tiny little star.
Yeah. So then they can be bigger.
Yeah.
So, what is it? The nebulosity surrounding a star is the star's shell or envelope of nebulosity, and a nebula is a giant cloud of dust and gas in space. Some nebulae, more than one nebula, come from the gas and dust thrown out by the explosion of a dying star, such as a supernova. Other nebulae are regions where new stars are beginning to form.
So how do they work? All stars form a nebulae, which are huge clouds of gas and dust. Inside stellar nebulae, space dust, hydrogen, helium, and plasma swirl around and stick together and form into large blobs. These blobs eventually collapse and the stuff inside begins to heat up. As more particles are pulled into the hot center, they eventually become a star. The process of star formation takes around 1 million years from the time the initial gas cloud starts to collapse until the star is created and shines like the sun. The leftover material from the star's birth is used to create planets and other objects that orbit the central star.
And then we're just gonna briefly go over so this is a series on NASA, just talking about how I think a planetary system is born and dies. It just goes over the whole birth of one, but for now we're just going to go over chapter 1 and chapter 2. So chapter 1 is A Star is Born, which is in their timeline 0 to 100,000 years. So as we know, the molecules of hydrogen and helium slow down and clump together because of gravity. Then there's tiny grains of silicates, iron, and carbon-rich material, which are together classified simply as dust, send some of the gas's energy back out into space, making the cloud even colder. So these clouds are very cold. So as we know, gravity plays a big part in kind of pulling everything together to form the star. While the infant star takes shape, the material spiraling inward flattens into a pancake-like structure known as an accretion disk. So how do we know what kind of star will form in these? And that is going to depend on the material available. So I'll just read this blurb here. Mysteriously, in our galaxy and probably most others, the likeliest type of star to form is almost too small to sustain itself. Red dwarfs, which can be between 1/13 to 1/2 of the mass of the sun, represent 3/4 of the stars in the Milky Way. Anything smaller than this, hydrogen will not be able to fuse in its core, which is, as we know, the dominant process that powers the stars. So red dwarfs burn so slowly that their lifetimes will be longer than that of the present-day universe. Sun-like stars are more rare. They represent 8% of the galaxy. And then even more rare are very massive stars, which can weigh as much as 150 suns and only live a few million years. And those are so big and luminous and so short-lived that astronomers are observing these stars in their pulsating, mass-ejecting death throes. while their low-mass stellar siblings are still in the process of forming. And a young star is called a protostar until it can power itself with hydrogen fusion reactions, and high temperature is crucial to that transition. So as the matter falls in faster and faster, the ball of gas at the center gets smaller and more compact. The tug of war between gravity and the other pressure heats up the infant star. The core of the star must get to about 10 million degrees before it becomes a hydrogen burning machine. And then to be a bona fide star, it must spontaneously fuse hydrogen atoms to form helium, releasing enormous amounts of energy. And then that energy helps stabilize the star's core so that it stops contracting, and that whole process can take about 40 million years. So then, with that, so that was chapter 1, and then I just have
40 million years?
Yeah, the whole process, I guess, can take about 40 million years.
Wow.
Which is, it's a long time.
Yeah.
And then I just have a little video. So NASA Solar System, Life and Death of a Planetary System, Chapter 1.
And that's a nebula.
Yes. So that was chapter 1. And then I'll just briefly go over chapter 2 here quick. And then we can watch this little chapter 2. So chapter 2 is from cloud to disk. So this is kind of talking about a newborn star and how it's shooting out violent jets of accelerated material as it gets nourishment from the gas and dust whirling around it. So their timeline for this phase is 100,000 to 1 million years.
Interesting.
And yeah, I guess really it just seems like the star in this phase per them is getting, like, it's like a little baby, you know? It's getting nourishment and everything from the surrounding gas and dust, and then it potentially, and then I guess here it says that about 100,000 years, the cloud starts to thin out enough to reveal 2 distinct structures, a newborn star and a fluffy, diffuse disk of gas. And then sometimes planets can form. But then we'll just watch this brief short video here on chapter 2. Maybe.
I do not hear anything.
Yeah, these ones don't have sound, I guess.
Okay, I just want to make sure.
Yeah. And I think that was the end of that one.
Cool.
And yeah, so that was just from NASA, little chapter 1 and 2, just briefly talking about kind of stellar nebulas and formation of stars. And average stars are also known as intermediate mass stars. These stars have lifetimes between 50 million and 20 billion years. These stars generate energy from the fusion of hydrogen to helium, then helium to carbon. And just in case you weren't aware, our sun is an average size star.
So, okay, any star which is larger than 8 solar masses during its regular main sequence lifetime is considered a massive star, and they typically have a quick main sequence phase, a short red supergiant phase, and a spectacular death via supernova explosion. In a massive star, hydrogen fusion in the core is followed by several fusion reactions involving heavier elements. Just before it exhausts all sources of energy, a massive star has an iron core surrounded by shells of silicon, sulfur, oxygen, neon, carbon, helium, and hydrogen. During the expansion, a dense layer of gas and dust is collected around the HII region, after which gravitational instabilities in the layer cause it to fragment into dense clumps, which then go on to collapse into new stars. The fragments are massive and thus form massive objects, stars or clusters. Although they're extremely rare, comparing less than 1% of the total stellar population, they make their presence known by dominating the surrounding interstellar medium, with the powerful stellar winds as well as shocks from their eventual supernova.
And then I just have a little thing here from NASA. It's a evolution of a massive star. So as we can see, protostar to a yellow bubble. So this series of images show 3 evolutionary phases of massive star formation from NASA's Spitzer Space Telescope. The stars start out in a thick cocoon of dust, evolve into hotter features dubbed yellow balls, and finally blow out cavities in the surrounding dust and gas, resulting in green-rimmed bubbles with red centers. So this process shown here takes roughly 1 million years. Even the oldest phase shown here is fairly young, as massive stars live a few million years. Eventually, the stars will migrate away from their birth clouds. So there's that
we
picture
gotta remember
there.
that what we're viewing now is what happened like probably at least millions of years ago, if not billions, just because of how far away this stuff is in light years.
Yes.
So like this isn't happening right this second. This already happened, what we're viewing.
Yeah. And yeah, that's interesting too.
Yeah.
An interesting fact or thing, I guess, to consider when viewing image, or even just talking about any of that
like
stuff.
What's going on in space and stuff.
Yeah.
I agree. And I did have the life cycle of our sun in an article as well. So our sun is a perfectly normal example of a G-type main sequence star, G2V, aka yellow dwarf. And like all stars, it has a lifespan characterized by a formation, main sequence, and eventual death. So the lifespan began roughly 4.6 billion years ago and will continue for another 4.5 to 5.5 billion years, when it will deplete its supply of hydrogen, helium, and collapse into a white dwarf. But this is just the abridged version of the sun's lifespan. So the sun is about halfway through the most stable part of its life. And it's remained relatively unchanged. This will stay the case for another 4 billion years, at which point it will have exhausted supply of hydrogen fuel. When that happens, some pretty drastic things are going to take place. So according to nebular theory, the sun and all planets of our solar system began as a giant cloud of molecular gas and dust. Then about 4.57 billion years ago, something happened that caused the cloud to collapse. It could have been the result of a passing star or shockwaves from a supernova, but the end result was a gravitational collapse at the center of the cloud. So the pockets of dust and gas began to collect in denser regions. So as denser regions pulled in more and more matter, conservation of momentum caused it to begin rotating, while increasing pressure caused it to heat up. Most of the material ended up in a ball at the center, while the rest of the matter flattened out into a disk that circled it. The ball would eventually be called the sun, while the disk material would form the planets. The sun was a collapsing protostar for about 100,000 years, before temperature and pressures in the interior ignited fusion at its core. The sun started as a T Tauri star, wildly active star that blasted out an intense solar wind. And just a few million years later, it settled down into its current form. So every second, 600 million tons of matter are converted into neutrinos, solar radiation, and roughly 4 times 10 to the 27th power watts of energy. For the sun, this process began 4.57 billion years ago, and it's been this way ever since. And as we talked about, there's a finite amount of hydrogen in the core of the sun, so it's not going to last forever. And the sun has been converted an estimated 100 times the mass of the Earth into helium and solar energy. As more hydrogen is converted into helium, the core continues to shrink, allowing the outer layers of the sun to move closer to the center and experience a stronger gravitational force. And this places pressure on the core, which is resisting by resulting increase in the rate with which fusion occurs. So the sun continues to expand hydrogen in its core, the fusion process speeds up and the output of the sun increases. So it leads to a 1% increase in luminosity every 100 million years and 30% increase over the course of the last 4.5 billion years. So in roughly 1 billion years, the sun will be 10% brighter than it is today. So Earth's atmosphere would absorb that heat energy, and it would trigger a moist greenhouse effect here on Earth, similar to what happened to Venus, looks like. In 3.5 billion years, the sun will be 40% brighter than it is now. The oceans will boil, the ice caps will permanently melt, and all water vapor in the atmosphere will be lost to space. You know, if we don't just do that ourselves first with global warming, but that's fine. Under these conditions, life as we know it won't be able to survive. And so it would be similar to Venus. Let's see, the core hydrogen exhaustion. With its hydrogen exhausted in the core, the inert helium ash that built up there will become unstable and collapse under its own weight. This will cause the core to heat up and get denser, causing the sun to grow inside and enter the red giant phase of evolution. So the sun would grow large enough to encompass the orbits of Mercury, Venus, and maybe even Earth. And then, of course, even if Earth survives, the heat's going to scorch our planet from that. So, and the final phase in death. So once it reaches the red giant branch phase, the sun will have about 120 million years of active life left. But a lot's going to happen during this time. The core will ignite violently into a helium flash, where 6% of the core and 40% of the sun's mass will be converted into carbon within a matter of minutes. The sun will then shrink around 10 times its current size and 50 times its luminosity, with a temperature a little lower than today. And then for the next 100 million years, it will continue to burn helium in its core until it's exhausted. And then it would be, after that, it would be in its asymptotic giant branch phase, where it will expand again much faster this time and become more luminous. In over 20 million years, the sun will become unstable and begin losing mass through a series of thermal pulses that'll occur every 100,000 years. They'll become larger each time and increase the sun's luminosity to 5,000 times its current brightness and its radius to over 1 AU. So the post-AGB evolution will be even faster as the ejected mass becomes ionized to form planetary nebula and the exposed core reaches 30,000 Kelvin. The final naked core temperature will be over 100,000 Kelvin, after which the remnant will cool towards a white dwarf. The planetary nebula will disperse in about 10,000 years, but the white dwarf will survive for trillions of years before fading to black. The ultimate fate of our sun. Our sun's not massive enough to make a supernova or a black hole. So given its mass, our sun will eventually collapse to a white star until it burns itself out. And of course, this won't be happening for another 6 billion years or so. And then by that point, humanity will either be, dead or have moved on from Earth. So we have plenty of days of sunshine to look forward to, it says. Lovely. So first, I'm going to just go over what different colors of stars mean. So red stars are the coolest, yellow stars are hotter than red stars, and white stars are hotter than red and yellow. but blue stars are the hottest stars of all.
And then we're going to go over Chapter 6 in that NASA Life and Birth of a Star System series, and that chapter is called Aging into a Red Giant. So I just have some points from that article here that I'll go over. So as our sun approaches its red giant phase, as we have talked about, it'll run out of fuel in its core. The core will get smaller as hydrogen fusion slows, leading it to heat up and kick off another round of nuclear reactions. This next round of nuclear reactions is the fusion of helium into heavier elements like carbon, nitrogen, and oxygen. Extra heat will cause the outer layer of gas to puff up, and they said that the end of a red giant phase is typically the most violent time in a star's life cycle. And here's a quote from astronomer Dmitry Veres from the University of Warwick. He said, "I am confident that the sun will swallow Mercury and Venus and not Mars, but the fate of the Earth, which resides in between, is less clear." And for some of you who may be worrying about this future fate of Earth, there's another quote from Mandel who said, "We will all be long gone. Earth won't be habitable, and the only chance for survival would be for an advanced civilization to migrate to a new planetary home." I don't know if that's reassuring, but, that's what we got.
Maybe
and
so maybe it'll happen.
The migration. Yeah, maybe. But either way, we won't be here when it turns into a red giant, so it won't affect us. Yeah. I don't know if that's a reassuring fact for people, but it's just the truth of the matter, So the planet's orbits may also become unstable during this time. As the red giant loses mass, the gravitational hold it has on planets becomes weaker. In our own solar system, the sun will throw off about half its mass, so the outer planet's orbits will drift outward, settling twice as far as they are today. Neptune, at 30 times the Earth's sun distance, will eventually hike out to about 60 times the Earth's sun distance. So, with that, I just have their video here from that series that I just wanted to briefly show. Let me get it going here. So, again, from NASA Solar System, Life and Death of a Planetary System, Chapter 6. And I don't think this one has sound either. That poor planet.
Oh no.
Okay, so that was that one. I think. Yeah, so that was just the, again, NASA series. That was Chapter 6 of that series.
Yeah, so let's talk a little bit more about red giants. So a red giant is a luminous giant star of lower intermediate mass and a late phase of stellar evolution. The outer atmosphere is inflated and tenuous, making the radius large and the surface temperature around 5,000 Kelvin or lower. Once at the red giant stage, a star might stay that way for up to 1 billion years. Then the star will slowly contract and cool to become a white dwarf. Earth-sized, ultra-dense star corpses radiating a tiny fraction of their original energy. So a red giant forms after a star has run out of hydrogen fuel for nuclear fusion and has begun the process of dying. The star maintains its stability through a fine balance between its own gravity, which holds it together, and the outwards pressure from ongoing thermonuclear fusion processes taking place at its core.
And then we'll briefly mention what a red supergiant is. So red supergiants are stars with a supergiant luminosity class of spectral type K or M, and they are the largest stars in the universe in terms of volume, although they are not the most massive or luminous. So then I have another brief little article here from, again, NASA. This is called The Symphony of Red Giant Stars. So, using observations from NASA's Transiting Exoplanet Survey Satellite, or TESS, astronomers have identified an unprecedented collection of pulsating red giant stars all across the sky. TESS primarily hunts for worlds beyond our solar system, also known as exoplanets, but its sensitive measurements of stellar brightness make TESS ideal for studying stellar oscillations, an area of research called asteroseismology. So I have another video here, and I'll just read like the description of what the video is. So this video is going to show, this visualization shows the new sample of oscillating red giant stars, the colored dots discovered by NASA's TESS. The colors map to each 24 by 96 degrees swath of the sky observed during the mission's first 2 years. The view then changes to show the positions of these stars within our galaxy, based on distances determined by ESA, or the European Space Agency's Gaia mission. The scale shows distance in kiloparsecs, each equal to 3,260 light years, and extends nearly 20,000 light years from the sun. So we'll watch that video here. I'm not sure if this one has sound. We'll find out. I don't think it does.
Interesting.
Okay. So that was that video. And then I have one more video from that article, and this one will have sound. So, and I'll just, again, give a brief description of the video. So, listen to the rhythms of 3 red giants in the constellation Draco, as determined by brightness measurements from NASA's Transiting Exoplanet Survey Satellite. To produce audible tones, astronomers multiplied the oscillation frequencies of the stars by 3 million times. It's clear that larger stars produce longer, deeper pulsations than smaller ones. So let's listen to some music produced by stars.
The last one just sounds like someone kind of messed up the mic, honestly.
Like this type thing, or
Yeah, or like they were
Okay.
messing with the mic or something. Yeah. But it's,
Yeah, it's
interesting. I
interesting.
wonder what makes them have different tones. Is it the size or?
I think that is from what at least that's what I understood from how they were explaining it,
Okay.
would be, I guess,
That would make sense.
yeah, because I guess then they're going to have different like fusion reactions going on based off of their different sizes.
Yeah.
Like even red giants, because I don't think every red giant is the exact same size, correct? Like they can be there can be variation.
Yeah, and I wonder if like they're all perfectly like circular, so to speak, with their matter, or if it's kind of like, you know, maybe there's like a little dent or something.
Yeah.
You know, like not a big dent, but just like, you know, little.
No, I know. Yeah, like a little
a perfectly
curvature. Yeah.
You're right. Because, I mean, yeah.
I would assume I would be very surprised to learn if every single star was a perfect sphere, like without any minor indent, or not big, but even just I'd be surprised if we were to draw a circle around the star, if every star was exactly circular and the same, without any alteration, Yes, yeah. I would be, I'm not going to say it's not, but I would be surprised.
Right. I would think the same thing. So let's start with the planetary nebula. So a planetary nebula is a type of emission nebula consisting of an expanding glowing shell of ionized gas ejected from red giant stars late in their lives. So we're going to watch a quick video here going over the different kinds of nebulae.
And it is from NASA Goddard, Hubble's Field Guide to Nebulae, whatever. We'll give it a watch.
The space between stars holds an array of vibrant clouds that command our attention, clouds that create spectacular displays, clouds that seem familiar, tenuous, and fragile, clouds that hold clues to star birth and death.
It's very
NASA's Hubble Space Telescope has imaged hundreds of them in extraordinary detail. These vast swirls of gas and dust get their name from the Latin word nebula, meaning cloud or mist. Nebulae is the plural of nebula, and they come in a wide range of shapes, sizes, and forms. Emission nebulae are some of the most spectacular. These opaque, gleaming clouds of gas and dust radiate or emit their own light. Ultraviolet light from nearby stars energizes atoms in the cloud. When the excited atoms lose that energy, they release the light that gives emission nebulae their glow. The Orion Nebula is one of the most famous emission nebulae. Its core, called the trapezium, holds 4 enormous young stars whose ultraviolet light powers the region's intense glow. The Carina Nebula is another vast emission nebula and star-forming region in our galaxy. Within the nebula is a pillar 3 light-years tall, dubbed Mystic Mountain. It cloaks massive young stars, some with jets emerging from the cloud. Hubble's infrared view cuts through the shroud of gas and dust, revealing these radiant jewels. Reflection nebulae shine by the reflected or scattered light of nearby stars. They often have a bluish color because the dust grains in the clouds scatter blue light more efficiently than red light. Not all nebulae shine brightly. Dark or absorption nebulae are inky black clouds of gas and dust that block the light coming from objects behind them. Because they are dark, absorption nebulae are hard to find. We only see them as silhouettes against a much brighter region of space. Most large nebulae are a combination of emission, reflection, and absorption nebulae. Their dark dust lanes may give birth to new stars that provide the light needed to illuminate the cloud. Planetary nebulae are a type of emission nebula powered by a small to medium-sized dying star. As these stars run out of fuel, they periodically blow off their outer layers. The expelled gas expands outward away from the star, forming a bubble or shell around the star. Sometimes, the envelope of debris holds clumps of dense gas that shine like the gems of a necklace. The term planetary nebula is misleading. It comes from late 18th century astronomers who thought their rounded shape looked similar to planets and telescopes of that time. They named them planetary nebulae as a result. Supernova remnants are the diffuse clouds of expanding debris released by a massive star's death explosion. The Cygnus Loop is a vast, expanding, 110 light-year wide supernova remnant. It is so large that Hubble can only image small sections of it at a time. Some supernova remnants emit their light from a shell of shocked material. Others, like the Crab Nebula, emit most of their light from within the expanding shell. And still other supernova remnants shine as a combination of the two. Nebulae are some of the most resplendent objects in the universe, and thanks to the Hubble Space Telescope, we can study them in all of their magnificent forms.
Pretty.
It is so pretty. Space. It's so pretty.
So, yes, it is. This might be a little repetitive, some of it, but I'm going to go over this article too. So nebulae are made up of gas, primarily hydrogen and helium, and fine cosmic dust. These clouds are part of the interstellar medium of extremely low density gas and dust that exists between stars in the void of space. Material so dispersed through the vastness of the cosmos that it can have a density as low as 0.1 atoms per cubic centimeter. In contrast, a cubic centimeter of the air we breathe on Earth would contain about 10 million trillion molecules. So, yes, it's like, what's the opposite of dense? It's the opposite of dense, whatever that word is. I can't think of it.
Light?
I guess, yeah. It's very light. Buoyant, maybe?
Maybe. I don't know, I guess.
I don't know if that applies in space, though, but anyways. Nebulae happen in places where the interstellar medium has become dense enough to form clouds. That could be because gravity has pulled the gas and dust together, or because stars have died and spewed their contents into the cosmos. Several types of nebulae exist, and each individual nebula is a unique showcase of the phenomena and process happening within. They often live side by side with smaller nebulae populating larger clouds of gas and dust to form giant complexes of star birth and death. So, okay, we've got emission nebulae, reflection nebulae, and planetary nebulae. And she also said the absorption nebulae, I think, but that article doesn't go over that one, I guess.
Oh.
So, all right. We've got emission nebulae. They're named because they emit their own light. This type of nebula forms when the intense radiation of stars within or near the nebula energizes the gas. The star's ultraviolet radiation floods the gas with so much energy that it strips electrons from the nebula's hydrogen atoms, a process called ionization. As the energized electrons revert from their higher energy state to a lower energy state by recombining with atoms, they emit energy in the form of light, causing the nebula's gas to glow. Interesting. So the reflection nebulae reflect the light from nearby stars. The stars that illuminate them aren't powerful enough to ionize the nebula's gas, as with emission nebulae, but their light scatters through the gas and dust, causing it to glow, like a flashlight beam shining on mist in the dark. That's a good visual. Planetary nebulae form during the death of low-mass to medium-mass stars. When such stars die, they expel their outer layers into space. These expanding shells of gas form a huge variety of unique shapes, such as rings, hourglasses, rectangles, and more, that show the complexity of stellar death. Astronomers are still studying how these intricate shapes form at the end of a star's life. And as the star casts off its outer layers, it leaves behind its core, which becomes a white dwarf star. And then we've got the next article. So a planetary nebula gallery. A planetary nebula represents a phase of stellar evolution that the sun should experience several billion years from now. When a star like the sun uses up all the hydrogen in its core, it expands into a red giant. In this phase, the star sheds most of its outer layers, even leaving behind a hot core that will soon contract to form a dense white dwarf star. A fast wind emanating from the hot core rams into the ejected atmosphere, pushes it outward and creates the graceful shell-like filamentary structures seen with optical telescopes. The diffuse X-ray emission seen in about 30% of the planetary nebulas in the New Chandra survey and all members of the gallery is caused by shock waves as the fast wind collides with the ejected atmosphere. The new survey data revealed that optical images of most planetary nebulae with diffuse X-ray emission displays compact shells with sharp rims surrounded by fainter halos. All of these compact shells have observed ages that are less than about 5,000 years, which therefore likely represents the timescale for the strong shock waves to occur. About half of the planetary nebulas in the study show X-ray point sources in the center, and all but one of these point sources show high-energy X-ray that may be caused by a companion star, suggesting that high frequency of central stars responsible for ejecting planetary nebulas have companions. Future studies should help clarify the role of double stars in determining the structure and evolution of planetary nebulas. All right, and then we're moving on to NASA's Webb captures dying stars' final performance in fine detail. 2 stars, which are locked in a tight orbit, shape the local landscape. Webb's infrared images feature new details in this complex system. The stars and their layers of light are prominent in the image from Webb's near-infrared camera on the left, while the image from Webb's mid-infrared instrument on the right shows the first time that the second star is surrounded by dust. The brighter star is in an earlier stage of stellar evolution and will probably eject its own planetary nebula in the future. In the meantime, the brighter star influences the nebula's appearance. As the pair continue to orbit one another, they stir the pot of gas and dust, causing asymmetrical patterns. Each shell represents an episode where the fainter star lost some of its mass. The widest shells of gas towards the outer areas of the image were ejected earlier. Those closest to the star are the most recent. Tracing these ejections allows researchers to look into the history of the system. And then we'll see the Hubble captures re-energized planetary nebula. Although the core of the star has stopped burning hydrogen and helium, a thermonuclear runaway at its surface ejects material at high speeds. This ejecta shocks and sweeps up the material of old nebula, producing the filaments and irregular shell around the central star seen in this image, which features data from the Hubble's Wide Field Camera 3 and the Panoramic Survey Telescope and Rapid Response System. And then we have planetary nebula NGC 2440. There's not much to say about this, but it's just really pretty to look at, honestly. And yeah, it just looks like there's a lot of...
Does it say what kind it is, I guess? What type of nebula it is? Or I guess it said planetary, right? Yeah.
I think it is a planet. Yeah, it is a planetary nebula. So there's that one. And then we've got the Hubble's view of planetary nebula reveals complex structure. NGC 6891 is made up of gas that's been ionized by the central white dwarf star, which stripped electrons from the nebula's hydrogen atoms. As the energized electrons revert from their higher energy state to a lower energy state by recombining with the hydrogen nuclei, they emit energy in the form of light, causing the nebula's gas to glow.
Okay. And then we're gonna move on to supernovas. So, have an article here from NASA. What is a supernova? A supernova is the explosion of a star, the largest explosion that takes place in space. And where do supernovas take place? Well, supernovas are often seen in other galaxies and are often difficult to see in our own Milky Way because dust blocks our view. And we may be wondering what causes them. So I guess in that article they mentioned that there were 2 types, and the first type of supernova happens in binary star systems. Binary stars are 2 stars that orbit the same point. One of the stars, a carbon-oxygen white dwarf, steals matter from its companion star. Eventually, the white dwarf accumulates too much matter. Having too much matter, it causes the star to explode, resulting in a supernova. The second type of supernova occurs at the end of a single star's lifetime. As the star runs out of nuclear fuel, some of its mass flows into its core. Eventually, the core is so heavy that it cannot withstand its own gravitational force. The core collapses, which results in the giant explosion of a supernova. The sun is a single star, but it does not have enough mass to become a supernova. And then we're also going to look here, another article from NASA. Hubble captures 3 phases of evolving supernova in the early universe. So, in this article, there were 3 different moments in a far-off supernova explosion that were captured in a single snapshot by NASA's Hubble Space Telescope. The star exploded more than 11 billion years ago, when the universe was less than a fifth of its current age of 13.8 billion years. And then with this one, we have a video, and the description for the video is: through a trick of light bending gravity, the Hubble Space Telescope captured 3 different moments in the explosion of a very far off supernova. So we'll watch that short video here too to kind of get a visual. So, and this is by NASA Goddard as well, and Hubble captures 3 phases of evolving supernova.
The Hubble Space Telescope captured 3 separate moments in a far-off supernova explosion in a single snapshot. These moments provide a unique glimpse into the supernova's early life. It is quite rare to detect a supernova explosion at a very early stage, because that stage is so short. It only lasts for hours to a few days, and it can be easily missed. The star exploded more than 11 billion years ago, when the universe was less than 1/5 of its current age of 13.8 billion years. In a single exposure, Hubble captured the supernova's rapid change of color, which indicates temperature change. The early, hotter phase appears blue. As the supernova cooled, its light turned redder. This detection was possible through a phenomenon called gravitational lensing, as first predicted by Einstein's theory of general relativity. In this case, the immense gravity of the galaxy cluster, Abell 370, both bent and magnified the light from the more distant supernova located behind the cluster, like a giant cosmic lens. This lensing effect split and warped the supernova's light, bending it along separate pathways of varying lengths. The different travel times between each path created a time delay that produced 3 distinct images of the explosion at different times that arrived at Earth simultaneously. This is the first detailed look at a supernova at such an early time of the universe's evolution. The research could help scientists learn more about the formation of stars and galaxies in the young universe.
Okay, interesting. It's kind of cool that they were able to capture like the 3.
Yeah.
And then I just have one more article here that is from NASA again, and it is Hubble reveals surviving companion star in aftermath of a supernova. So we'll just read here. NASA's Hubble Space Telescope has uncovered a witness at the scene of the star's explosive death, a companion star previously hidden in the glare of its partner supernova. The discovery is a first for a particular type of supernova, one in which the star was stripped of its entire outer gas envelope before exploding. The finding provides crucial insight into the binary nature of massive stars, as well as the potential prequel to the ultimate merger of the companion stars that would rattle across the universe as gravitational waves, ripples in the fabric of space-time itself. And then there's this image here. It's this artist illustration, shows supernova 22013 GE with its companion star in the lower right. Companion star is impacted by the blast wave from the supernova, but not destroyed. Over time, astronomers observed the ultraviolet UV light of the supernova fading, revealing a nearby second source of UV light that maintained brightness. The theory is that the 2 massive stars evolved together as a binary pair, and that the current survivor siphoned off its partner's outer hydrogen gas shell before it exploded. Eventually, the companion star will also go supernova.
Ooh, interesting.
Yeah, so it's interesting that, like, the star, I guess it makes sense kind of that the star didn't get disintegrated, but it's just interesting that it survived the blast of the supernova, you know? That's just...
Yes.
And it like took in that and like siphoned off it stole the energy from its brother, I guess, if you will.
Yeah, we can call them brothers.
Yeah. And then there's another picture in this article, the evolution scenario for a stripped envelope supernova. So this infographic shows the evolution astronomers propose for supernova 2013 GE, which is the one we just went over. Panels 1 through 3 show what has already occurred, and panels 4 through 6 show what may take place in the future. So the first image, a binary pair of massive stars orbit one another. In the second image, one star ages into its red giant stage, getting a puffy outer envelope of hydrogen that its companion star siphons off with gravity. Astronomers propose this is why Hubble found no trace of hydrogen in the supernova debris. 3. The stripped envelope star goes supernova, jostling but not destroying its companion star. After the supernova, the dense core of the former massive star remains either as a neutron star or black hole. 4. Eventually the companion star also ages into a red giant, maintaining its outer envelope, some of which came from its companion. 5. The companion star also undergoes a supernova. And then 6. If the stars were close enough to each other not to be flung from their orbits by the supernova blast wave, the remnant cores will continue to orbit one another and eventually merge, creating gravitational waves in the process.
That's interesting.
Yeah, so that'll be interesting. Like, I don't think we'll probably be around then, but...
Well, it's probably happening right now. We're just not capturing
it. Yeah, but we won't see
so far away.
Yeah.
We won't see it in our lifetime, though.
Unfortunately. I mean, unless we reverse aging or something, you know? But even then, our star might get us then.
Yeah, the sun might get us first.
Yeah. So, to start that off, we're just going to be looking at the next chapter in that series, NASA's series, Life and Death of Planetary System. We're going to look at chapter 7, which is Death and New Life. And their time frame for that is 11 to 13 billion years. So, when the core of the former red giant has exhausted all of its fuel and shed all the gas it can, the remaining dense stellar cinder is called a white dwarf. The white dwarf is considered dead because atoms inside of it no longer fuse to give the star energy, but it still shines because it is so hot. Eventually, it'll cool off and fade from view. Our sun will reach this death about 8 billion years from now. And then we're just going to watch the short little video with that here.
Wow. What was that?
Okay. We'll find out. But that was chapter 7.
Yeah. That's cool. They said like the death brings new life.
Yeah, and then starts the cycle all over again.
Yeah.
It's kind of interesting how that's like...
I feel like that's just kind of like how the universe is in general.
Cyclical like that?
Yes, exactly. So next we're going to look at white dwarfs. So the first article is white dwarf stars. These are from NASA. So Pushing the limits of its powerful vision, NASA's Hubble Space Telescope uncovered the oldest burned-out stars in our Milky Way galaxy. These extremely old, dim clockwork stars provide a completely independent reading on the age of the universe. The ancient white dwarf stars as seen by Hubble are 12 to 13 billion years old, because earlier Hubble observations show that the first stars formed less than 1 billion years after the universe's birth in the Big Bang. Finding the oldest stars puts astronomers well within arm's reach of calculating the absolute age of the universe. So we've got another article about white dwarf stars. So white dwarf is what stars like the sun become after they've exhausted their nuclear fuel. Near the end of its nuclear burning stage, this type of star expels most of its outer material, creating a planetary nebula. Only the hot core of the star remains. The core becomes a very hot white dwarf with a temperature exceeding 100,000 Kelvin. Unless it is accreting matter from a nearby star, see cataclysmic variables. The white dwarf cools down over the next billion years or so. And because a white dwarf is not able to create internal pressure, gravity compacts the matter inward until even the electrons that compose a white dwarf's atoms are smashed together. So in normal circumstances, identical electrons, or those with the same spin, are not allowed to occupy the same energy level. Since there are only two ways an electron can spin, only two electrons can occupy a single energy level. This is what is known in physics as Pauli exclusion principle. So in a normal gas, this isn't a problem because there aren't enough electrons floating around to fill up the energy levels completely. But in a white dwarf, the density is much higher and all of the electrons are much closer together. This is referred to as a degenerate gas, meaning that all the energy levels in its atoms are filled up with electrons. So for gravity to compress the white dwarf further, it must force electrons where they cannot go. Once a star is degenerate, gravity cannot compress it anymore because quantum mechanics dictates that there is no more available space to be taken up. So our white dwarf survives not by internal fusion, but by quantum mechanical principles that prevent its complete collapse. And then degenerate matter has other unusual properties, like the more massive a white dwarf is, the smaller it is. And this is because the more mass a white dwarf has, the more its electrons must squeeze together to maintain enough outward pressure to support the extra mass. However, there is a limit on the amount of mass a white dwarf can have. I'm not going to try to pronounce this name, but Chandrasekhar discovered this limit to be 1.4 times the mass of the sun. This is appropriately known as the Chandrasekhar limit. The heavier atoms in its atmosphere sink and the lighter ones remain at the surface. Some white dwarfs have almost pure hydrogen or helium atmospheres, the lightest of elements. Also, gravity pulls the atmosphere close around it into a very thin layer. So next, we have Hubble discovers hydrogen burning white dwarfs enjoying slow aging. So now an international group of astronomers has discovered the first evidence that white dwarfs can slow down their rate of aging by burning hydrogen on their surfaces. We found that the first observable evidence that white dwarfs can still undergo stable thermonuclear activity, explained Jianqing Chen of the alma mater Studiorum Università di Bologna and the Italian National Institute for Astrophysics, who led this research. This was quite a surprise, as it is at odds with what is commonly believed. So, this discovery could have consequences for how astronomers measure the age of stars in the Milky Way galaxy. The evolution of white dwarfs has previously been modeled as a predictable cooling process. This relatively straightforward relationship between age and temperature has led astronomers to use white dwarf cooling rate as a natural clock to determine the age of star clusters, particularly global and open star clusters. However, white dwarfs burning hydrogen could cause these age estimates to be inaccurate by as much as 1 billion years. And then lastly, there was a citizen scientist who found an ancient white dwarf star encircled by puzzling rings. And this white dwarf is so old that whatever process is feeding material into its rings must operate on billion-year timescales. said John Deebs, an astronomer at the Space Telescope Science Institute in Baltimore. Most of the models scientists have created to explain rings around white dwarfs only work well up to around 100 million years, so this star is really challenging our assumptions on how planetary systems evolve. Previously, disks and rings had only been observed surrounding white dwarfs around 1/3 of this star's age. Yet some white dwarfs, between 1 and 4%, show infrared emissions indicating that they're surrounded by dusty disks or rings. Scientists think the dust may arise from distant asteroids and comets kicked closer to the star by gravitational interactions with displaced planets. As these small bodies approach the white dwarf, the star's strong gravity tears them apart in a process called tidal disruption. The debris forms a ring of dust that will slowly spiral down onto the surface of the star.
Okay. And then next we're going to just move on to neutron stars. So my first article I have here again is from NASA, just about neutron stars. So when the core of a massive star undergoes gravitational collapse at the end of its life, protons and electrons are literally scrunched together, leaving behind one of nature's most wondrous creations, a neutron star. Neutron stars cram roughly 1.3 to 2.5 solar masses into a city-sized sphere, perhaps 20 kilometers or 12 miles across. Matter is packed so tightly that a sugar cube-size amount of material would weigh more than 1 billion tons, about the same as Mount Everest. So most known neutron stars belong to a subclass known as pulsars. These relatively young objects rotate extremely rapidly, with some spinning faster than a kitchen blender. They beam radio waves in narrow cones, which periodically sweep across Earth like lighthouse beacons. And astronomers have found less than 2,000 pulsars, yet there should be about 1 billion neutron stars in our Milky Way galaxy. There are 2 reasons they have for this shortfall. One is age. Most neutron stars are billions of years old, which means they have plenty of time to cool and spin down. Without much available energy to power emissions at various wavelengths, they have faded to near invisibility. But even many young pulsars are invisible to us with radio telescopes because of their narrow lighthouse beams. Because pulsar beams are much broader and gamma rays, GLAST will allow us to detect some of the youngest, most energetic pulsars in our galaxy, says GLAST interdisciplinary scientist Stephen Thorsett of the University of California, Santa Cruz. Getting a much more complete sample of the Milky Way's population of neutron stars is one of the most important ways that GLAST will advance their understanding of the life cycle of stars. And GLAST is... I thought it said somewhere, but I'm guessing it's one of like their telescope monitoring.
Yeah, I would think
something like that. Yeah. So then the next article I have here is again from NASA, and it's NASA's retired Compton mission reveals super heavy neutron stars. So astronomers studying archival observations of powerful explosions called short gamma ray bursts, or GRBs, have detected light patterns indicating the brief existence of a super heavy neutron star shortly before it collapsed into a black hole. This fleeting massive object likely formed from the collision of 2 neutron stars. And they looked for these signals in 700 short GRBs detected with NASA's Neil Gell Swift Observatory, Fermi Gamma Ray Space Telescope, and the Compton Gamma Ray Observatory, explained Cecilia Sciurenti, a researcher at the University of Maryland College Park and NASA's Goddard Space Flight Center in Greenbelt, Maryland, who presented the findings at the 241st meeting of the American Astronomical Society in Seattle. They found these gamma ray patterns in 2 bursts observed by Compton in early 1990s. So, with this article, we have a video. And the video is a simulation that tracks the gravitational wave and density changes as 2 orbiting neutron stars crash together. Dark purple colors represent the lowest densities. White, yellow, white shows the highest. An audible tone and a visual frequency track the track the steady rise in the frequency of gravitational waves as the neutron stars close. When the objects merge at 42 seconds, the gravitational waves suddenly jump to frequencies of thousands of hertz and bounce between two primary tones. The presence of these signals in such simulations led to the search and discovery of similar phenomena in the light emitted by short gamma ray bursts. So we'll watch that short video here. Okay. Oops. Okay. Interesting.
Yeah.
And then we'll move on to the next article, again from NASA. So, this is NASA's NICER probes the squeezability of neutron stars. So, matter in the hearts of neutron stars, dense remnants of exploded massive stars, takes the most extreme form we can measure. Now, thanks to data from NASA's Neutron Star Interior Composition Explorer, or NICER, an X-ray telescope on the International Space Station, scientists have discovered that this mysterious matter is less squeezable than some physicists predicted. This finding is based on NICER's observation of PSR J0740 plus 6620, J0740 for short, the most massive known neutron star, which lies over 3,600 light years away in the northern constellation Camelopardalis. So J0740 is in a binary star system with a white dwarf, the cooling remnant of a sun-like star, and rotates 346 times per second. Previous observations place the neutron star's mass at about 2.1 times the sun. So with that, we have another video here, and it's going to watch how NASA's neutron star, NICER, is helping physicists peer into the hearts of neutron stars, the remains of massive stars that exploded in supernovae. Scientists want to explore the nature of matter inside these objects, where it exists on the verge of collapsing into black holes. To do so, scientists need precise measurements of neutron stars' masses and sizes, which NICER and other efforts are now making possible. So, NASA's NICER tests matter's limits by NASA Goddard.
Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered about the properties of that matter, the densest in the universe we can measure, and what form it takes. Now they have new insights thanks to NASA's NICER X-ray telescope on the International Space Station. A neutron star forms when a massive star's core runs out of fuel. With nothing left to fight gravity, the star collapses. Here, protons and electrons crush together to form neutrons, as well as lightweight particles called neutrinos that escape the star. The core continues to collapse until the matter at its center has twice the density of an atom's nucleus, but on a city-sized scale. When the core can't compress further, it rebounds. The expanding core crashes into the star's collapsing inner layers, creating a shockwave that rips outward through the star. The result is a powerful supernova explosion with a newborn neutron star at its center. Scientists have many questions about neutron star physics, including how squeezable is the matter in their cores? In more squeezable models, the internal pressure and density break neutrons in the center into a sea of even tinier particles, or combinations of those particles, resulting in a squishy core and a smaller star for a given mass. In some less squeezable models, the neutrons hold up against those forces, resulting in a larger star. Scientists used NICER's precise mass and size measurements of two pulsars, a kind of rapidly rotating neutron star, to narrow down how compressible these objects are. The pulsar is so dense that its strong gravity warps nearby spacetime, allowing us to see light emitted from its far side. This distortion makes it look bigger than it actually is. The more massive the pulsar, the greater the warping and the larger it appears. Scientists measure this distortion by tracking the brightness of X-ray emitting hotspots on the pulsar's surface as it spins. They can then precisely determine the pulsar's mass and radius and obtain important clues about conditions in the core. NICER used this method to analyze J0740, the heaviest known pulsar with about 2.1 times the Sun's mass. Two research groups using different approaches both estimate it's about 16 miles across. NICER's measurements of J0740 and pulsar J0030 disfavor squeezable models, where cores contain only quarks or other exotic matter. And J0740's size and mass together challenge less squeezable theories, where cores contain only neutrons. Physicists will have to develop new models, perhaps containing both neutrons and quarks, to explain NICER's observations. The cores of neutron stars represent matter's final, stable form, short of becoming a black hole. Scientists can't recreate those conditions in Earth laboratories, so NICER will continue to measure pulsars to probe deeper and deeper into the hearts of these mysterious objects.
Okay. Oh,
Just-
interesting. I always like how, like, they can always end up finding new, like, things, unexpected things, you know, like how
Yeah.
this doesn't match either of their models, so now they kind of have to come up with a new model theory. I always find that, I love science like that, where sometimes we don't know, you know, and we think we know, and then
Yeah.
we find out what our theories weren't exactly right, so then we have to adjust them a little bit, and that's always interesting.
Right. And then we find that through a lot of, testing and math and
Yes.
all that fun stuff.
And then I have a couple more articles here from NASA. This one is Powerful Neutron Stars Behavior, Surprise IXPE Researchers. So in February of 2022, NASA's Imaging X-ray Polarimetry Explorer, IXPE, observed its first accreting neutron star, Hercules X1, more than 21,000 light-years from Earth. Now, a new study based on those observations has upended traditional assumptions about neutron stars and their interior processes that drive these ultra-powerful objects. So, Hercules X1 isn't alone in space. It has companions, star in close proximity, and because of its powerful gravity, strips that neighbor of its outer layer of gas. That feature makes it an accreting neutron star, meaning it pulls streams of hijacked energy and particulate matter from the so-called donor star. It's dragged along the neutron star's own intense magnetic field lines and forms an accretion disk around Hercules X1. So Hercules X1 is also a pulsar. Pulsars are neutron stars which rotate faster and faster as their cores collapse, emitting powerful beams of electromagnetic radiation. These energetic strobes register as pulses detectable across distances of thousands of light years by IXPE and other telescopes. So scientists know a lot about the strength of a neutron star's magnetic field, Hurt noted, but have yet to fully grasp the physical structure of that field, how and why it fluctuates over time, and the relationship between a accreting neutron star and its donor star. And that is where IXPE really shines, said Brian Ramsey, IXPE principal investigator at Marshall. The effects we infer from polarization are impossible to see directly, operating on scales we could never hope to capture using conventional means. IXPE is helping us document the behavior of the invisible world. So, such a large discrepancy implies that our ideas about how X-rays are generated in Hercules X1 and possibly other pulsars will need to be substantially revised, said Juri Poutanen of the University of Turku, Finland, who leads IXPE research into accreting neutron stars. The system has previously showed regular variations in brightness with a period of 35 days. Despite two stars orbiting each other every 1.7 days, such fluctuation could indicate what is known in astrophysics as precession, an ongoing process of slow changes to a celestial body's orbital or rotational parameters. In other words, the accretion disk could be warped or wobbling as it spins. So, yeah, just kind of some new stuff they're learning about neutron stars. And then the last little article here from NASA again is astronomers spot a distant and lonely neutron star. So they have discovered, and astronomers have discovered a special kind of neutron star for the first time outside the Milky Way galaxy. Neutron stars are the ultra-dense cores of massive stars that collapse. This newly identified neutron star is a rare variety that has both a low magnetic field and no stellar companion. It's located within the remains of a supernova in the small Magellanic Cloud located 200,000 light years from Earth. Oxygen-rich supernova remnants are important for understanding how massive stars fuse lighter elements into heavier ones before they explode. Seen up to a few thousand years after the original explosion, oxygen-rich remnants contain the debris ejected from the dead star's interior. This debris is observed today hurtling through space after being expelled at millions of light years per hour. The lack of evidence for extended radio emissions or pulsed X-ray radiation, typically associated with rapidly rotating, highly magnetized neutron stars, indicates that astronomers have detected the X radiation from the hot surface of an isolated neutron star with low magnetic fields. About 10 such objects have been detected in the Milky Way galaxy, but this is the first one detected outside our galaxy. But how did this neutron star end up in its current position? Seemingly offset from the center of the circular shell of X-ray emission produced by the blast wave of the supernova. One possibility is that the supernova explosion did occur near the middle of the remnant, but the neutron star was kicked away from the site in an asymmetric explosion at a high speed of about 2 million miles per hour. However, in this scenario, it is difficult to explain why the neutron star today is so neatly encircled by the recently discovered ring of gas seen at optical wavelengths. Another possible explanation is that the neutron star is moving slowly and its current position is roughly where the supernova explosion happened. In this case, the material in the optical ring may have been ejected either during the supernova explosion or by the doomed progenitor star up to a few thousand years before. So, yeah, just a lonely neutron star, and they're wondering why. Trying to figure out why. But yeah, so that's some articles that we had on neutron stars.
Right, and now we can move on to black holes. So what is a black hole? A black hole is an astronomical object with gravitational pull so strong that nothing, not even light, can escape it. A black hole's surface is called its event horizon, and it defines the boundary where velocity needed to escape exceeds the speed of light, which is the speed limit of the cosmos. Matter and radiation fall in, but they can't get out. So two main classes of black holes have been extensively observed. Stellar mass black holes with 3 to dozens of times the sun's mass are spread throughout the Milky Way galaxy, while supermassive monsters weighing 100,000 to billions of solar masses are found in the centers of most big galaxies, including ours. So a stellar mass black hole forms when a star with more than 20 solar masses exhausts the nuclear fuel in its core and collapses under its own weight. The collapse triggers a supernova explosion that blows off the star's outer layers, but if the crust core contains more than about 3 times the sun's mass, no known force can stop its collapse to a black hole. The origin of supermassive black holes is poorly understood, but we know they exist from the very earliest days of a galaxy's lifetime. Once born, black holes can grow by accreting matter that falls into them, including gas stripped from neighboring stars and even other black holes. Although light can't escape a black hole's event horizon, the enormous tidal forces in its vicinity cause nearby matter to heat up to millions of degrees and emit radio waves and X-rays. Some of the material orbiting even closer to the event horizon may be hurled out, forming jets of particles moving near the speed of light that emit radio, X-rays, and gamma rays. Jets from supermassive black holes can extend hundreds of thousands of light years into space. Interesting. So the next article, the Hubble finds hungry black hole twisting captured star to donut shape. I believe we have a video for that.
Yes. So this video is Hubble finds hungry black hole twisting captured star into donut by NASA Goddard. And we'll watch that here.
Using NASA's Hubble Space Telescope, have recorded a star's final moments in detail as it was ripped apart and eaten up by a black hole in a tidal disruption event. The shredded star is nearly 300 million light years away, but astronomers used Hubble's powerful ultraviolet sensitivity to analyze its light to gather forensic clues of the violent event. Hubble data found a very bright, hot, donut-shaped area of gas the size of the solar system swirling around a black hole. The swirling gas was once a star.
Can you pause?
Usually, astronomers get just a few...
Yes.
Something I just realized to help remember. So there's infrared and ultraviolet. Like, I'm just now realizing that it's infrared and ultraviolet because they're on the ends of the color spectrum. So like red is on one end of the color spectrum and violet is on the other end.
Oh.
So it's infrared and ultraviolet. That's why it's those two.
Oh. I never knew that either.
I just realized it now, so I was just looking at this color scale or whatever. And yeah.
I didn't even notice that either, but yeah, no, I didn't know that, so now we all learned, or maybe not some, but we learned something new, so.
Yeah, we learned this together.
Few observations at the beginning of a disruption event when it's very bright, but this energetic collision's proximity and brightness allowed Hubble to gather ultraviolet data over a longer than normal time period. This is a rare opportunity for scientists to create models of what they think is going on and then compare those models with what Hubble sees. It is an exciting place for scientists to be, right at the intersection of the known and the unknown.
Okay.
Cool. All right, so black holes are gatherers and not hunters. They're going to lie in wait until a helpless star wanders by. When the star gets close enough, the black hole's gravitational grasp violently rips it apart and sloppily devours its gases while belching out intense radiation. These are termed tidal disruption events, but the wording belies the complex raw violence of a black hole encounter. There's a balance between the black hole's gravity pulling in star stuff and radiation blowing material out. So in other words, black holes are messy eaters. Astronomers are using Hubble to find out the details of what happens when a wayward star plunges into the gravitational abyss. And then we've got new NASA black hole sonifications with the remix. We've got 2 videos for that.
So the first one is data sonification, black hole at the center of the Perseus galaxy.
Creepy.
Right?
So cool.
And then the second one we have is data sonification, black hole at the center of galaxy M87. That one was so much more calming.
Yeah, that's so weird.
Yeah, it's
They all
interesting.
sound so different.
Yeah, that's very interesting.
Yes. So, okay, there's a popular misconception that there is no sound in space, and it originates with the fact that most of space is essentially a vacuum, and that provides no medium for sound waves to propagate through. But a galaxy cluster, on the other hand, has copious amounts of gas that envelop the hundreds or even thousands of galaxies within it, and that provides a medium for the sound waves to travel. In this new sonification of Perseus, the sound waves astronomers previously identified were extracted and made audible for the first time. So the sound waves were extracted in radial directions, that is, outwards from the center. The signals were then resynthesized into the range of human hearing by scaling them upwards by 57 and 58 octaves above their true pitch. So another way to put this is that they're being heard 144 quadrillion and 288 quadrillion times higher than their original frequency. The radar-like scan around the image allows you to hear waves emitted in different directions. So then we have one more article here, and that is the Hubble determines mass of isolated black hole roaming our Milky Way galaxy. There's a video with this one as well.
And that is Hubble measures potential isolated black hole roaming galaxy by NASA Goddard.
Black holes roam our Milky Way galaxy. These objects are invisible and so very difficult to detect. Astronomers now believe they may have precisely measured the mass of an isolated black hole for the first time. After 6 years of observations, NASA's Hubble Space Telescope found evidence for a lone black hole about 5,000 light-years away, wandering through interstellar space. Black holes roaming our galaxy are born from rare monstrous stars, less than 1,000th of the galaxy's stellar population, that are many times more massive than our Sun. These stars die in supernova explosions, their cores crushed by the star's own gravity into a black hole. Because the detonation is asymmetrical, the black hole may get a kick, sending it careening through our galaxy. Hubble detected the magnified and deflected light from a star lined up exactly behind the potential black hole, as its intense gravity warps space itself. The measurements indicate the black hole weighs 7 solar masses and is traveling through space at 100,000 miles per hour. But don't worry, there's a lot of space between Earth and this roaming black hole.
Okay.
All right. So yeah, astronomers estimate that 100 million black holes roam among the stars in our Milky Way galaxy, but they never have conclusively identified an isolated black hole before. Following 6 years of meticulous observations, the Hubble Space Telescope has, for the first time ever, provided direct evidence for a lone black hole drifting through interstellar space by a precise mass measurement of the phantom object. Until now, all black hole masses have been infrared statistically, or through interactions in a binary system or in the cores of galaxies. Stellar mass black holes are usually found with companion stars, making this one unusual. The signature of a foreground black hole stands out as unique among other microlensing events. The very intense gravity of the black hole will stretch out the duration of the lensing event for over 200 days. Also, if the intervening object was instead a foreground star, it would cause a transient color change in the starlight as measured because the light from the foreground and background stars would momentarily be blended together. But no color change was seen in the black hole event. And the existence of stellar mass black holes had been known since the early 70s, but all their mass measurements until now have been in binary star systems. Gas from the companion stars falls into the black hole and is heated to such high temperatures that it emits X-rays. About 24 black holes have had their masses measured in X-ray binaries through their gravitational effect on their companions. Mass estimates range from 5 to 20 solar masses. Black holes detected in other galaxies by gravitational waves from mergers between black holes and companion objects have been as high as 90 solar masses.
So, we'll just kind of go over briefly the star's life cycle, which is So as we mentioned, the stellar nebula is a birthplace of stars. Stars can be either average or massive. Then they can turn into red giants or super red giants. Planetary nebulas are ejected from red giants later in their life. Stars can also go supernova later in life. Then the last stages of a star's life include white dwarfs, neutron stars, and black holes. And with that, we are just going to watch a video here from NASA. And it is Life and Death of a Planetary System by NASA Solar System.
Is that the one we watched before?
I had parts of it.
Okay. So I say
that was like the whole chapter, the whole series. Yeah.
Okay. That's pretty cool. Had some good visuals and everything though. So, okay, a star like the sun lives for 10 billion years. Yeah, I just think it's interesting. It's about halfway through its life cycle. It's 4.6 billion years old.
Yeah, that is. It's crazy to just think about, like.
That's so much time.
Yeah, and I don't even know if we can actually, like, grasp that amount of time. Like, I mean, we can, like, sit here and be like, oh yeah, that's a lot of time, but I don't think we can actually, like,
we can't
grasp it in turn. Yeah, it's hard to. I mean, you could always, like, I think in the series, what is that one show called where they, I think it's with Neil deGrasse Tyson.
Oh, like the
Cosmos, yeah. He kind of they break it down into a calendar, but it's like a 12-year calendar.
Yeah.
But even with that, we're at like on December 31st, like at our point in time. So it's still hard to actually it's crazy.
Yeah. I mean, the way I kind of think of it, it's kind of like, I don't know, freaks me out a little bit because like it makes me think of like the ocean, how deep it is. And that freaks me out a lot. Like, that's just one of my biggest fears. But, like, and thinking about time that way, because it's just so, like, immeasurable. Like, I feel like the ocean's kind of the same.
Okay.
Where, like, you don't really understand how deep the ocean is until you're in there. You know?
Yeah, or like how big it is just in general.
Yeah, and how big, like, you know, whales
Like if you're
are.
in the middle of the ocean.
Yeah.
Ugh.
But yeah, just like how deep it goes. Like, it's kind of like time is the same way for the universe.
Yeah,
You know,
I guess I've
like,
never thought of it like that, but that makes sense.
Yeah. I don't know. That's just how I'm trying to think of it so I can try to comprehend it. And like it's really old.
Yes.
But yeah, and the sun is a main sequence star, and it generates energy through the nuclear fusion of hydrogen nuclei into helium. And okay, so what is fusion? It occurs when two atoms slam together to form a heavier atom, like when two hydrogen atoms fuse to form one helium atom. And this is the same process that powers the sun and creates huge amounts of energy. And this is several times greater than fission. And fission is the splitting of atoms, either by radioactive decay or by collisional impact. Certainly, radioactive decay occurs because the sun contains many radioactive isotopes, including thorium, uranium, and more. So we have one last video here, and it's just kind of to understand the size of these stars and the universe in general. So
this universe size comparison 3D by Harry Everett.
yes, that's the one. If you want to, you can play it at like 1.5 speed.
We can.
Or like 2 speed, even if you want.
Because there's no like talking.
Right. It's just seeing the size, I think.
Okay.
It would make it easier to
I'll pause it quick. I didn't realize Mars was smaller than Earth, if I'm going to be honest.
Yeah, no. Mars is smaller than Earth. It's a rocky planet. I think Earth
Yeah, I guess. Because then I was in my head, I was like, how are we going to, in theory, colonize Mars if it's so much smaller? But Earth is a lot of water, though. There's like, Mars would be a lot more land for us to have like space, you know, I guess. Even if it is smaller, there's still more like land.
Yeah.
Comparatively. I would think. Or maybe it's the same size of the continents all put together on Earth. I don't know, I guess. But
yeah. Well, the moon would be a lot easier to go to than Mars, though. Because it's just so much closer.
Yeah.
It takes less resources to get there, and like we know more about it.
We can colonize
have
both.
The rover. Yeah, I just think going straight to Mars is a bad idea.
Oh yeah, I mean,
isn't that like Elon Musk's idea?
That I don't know. I don't know.
I know he's trying to go to Mars.
Yeah, I think that
did some about that.
I think that's a big thing of his, but I guess I don't know where that's at on his list of priorities right now. But
yeah, he's got so many things he's involved in.
Yeah.
But I mean,
yeah. We'll keep seeing how much bigger it gets here.
Okay, pause it for a sec. Oh my god, it disappeared. Like, where even is Earth anymore, though? You know? It's so,
Yeah, because you can't see it.
it's so small, yeah.
Keep going.
Let's keep going.
Okay.
Wait, is that a black hole?
They must be.
Oh my god, they're so big.
Whoa.
Oh wow. I didn't realize. Oh my gosh. Oh,
What is this? Oh,
the universe.
okay.
Wow.
That was. I like it.
Yeah.
It's kind of a little just crazy to think about, but
It's so big.
it is. And we're so tiny. We're like ant. We're not even ants. We're smaller than ants in the grand scheme
We're
of the
like
universe.
little single cell organisms.
We are. We're like the bacteria in our guts. We're like that to the universe.
Pretty much.
It's very interesting to think about. And especially because stars aren't solid, you know?
Yeah.
So it's
just
all
a bunch
this.
of energy.
Yeah.
It's like,
But obviously, if you were to go try swimming in that energy, I don't.
I mean, you probably get burned alive.
Yeah.
You know?
And then just knowing, like how we learned in black holes, that there's just black holes roaming around, like,
Right.
cool. Space. It's very interesting.
Yeah.
And how
Okay,
we're.
Sometimes I freak out a little bit because, like, what if a black hole just decided to come this way, you know? Like, we couldn't do anything about it.
Yeah.
It just happened.
Yeah. And. Yeah, it's just luck, I guess. We're just very lucky that the star formation of our planet happened the way it did and that black holes don't roam.
Yeah,
near us, you know?
spot.
We're very lucky. I mean, not that this is the only spot, obviously, but just the fact that we are here, I guess, is pretty lucky.
Yeah.
But yeah, it'll be interesting to see if we try to call it, because even if we call it, like, so let's say we do solve quote unquote solve aging. I mean, aging itself isn't a problem, but I guess some people want to live forever, you know. So we fix that issue of death from aging. Obviously, we'd still have other causes of death as the way of life.
If we did that, we'd have too many people, because people would still, like, you know, have babies and stuff.
True, but let's not factor that in. We're not going to worry about that. We're going to pretend that doesn't exist.
We're going
to.
Yeah.
Okay. We can bring that equation into that is important, but that isn't the point I was going towards. But we can talk about that. But what I was thinking is, even if we do solve that and we solve the problem of overpopulation, we'll assume we solve that problem too, to make my point easier. And then let's say we colonized the moon and we colonized Mars. The Earth, like, we still have to get out of this solar system to survive when it turns into a red giant, you know? Like, I don't think going to Mars is going to be enough, even if we figure that out.
Yeah.
And I think they are looking for exoplanets too, though. But
yeah,
it's just interesting.
I think they have found Earth-like planets like really far away.
So then it's the engineering of how to get there.
Yeah.
And like stasis, or I guess if we cure aging, like death from aging, then people could stay not in a cryostasis state the whole trip. Well, but then it'd probably still be more efficient to put them in cryostasis for food wise, though, so that they don't have to pack that much food, unless we solve the problem of eating to where people don't even need to eat anymore, Well, I guess that could just be pills, like little pills that are your meal, like for a week or something. But
yeah,
I think space will still win eventually. We can't solve space,
Yeah, they have found Earth-like planets, so.
Have they?
I looked it up, yes.
Does it say how far they are?
This one I found is 100 light years away. So, like, that'd be like a generation or two. That'd be a couple generations.
Okay. Yeah. But it's also, with how you mentioned, we don't see it as it is now. We only see it how it was in the past.
That's true, too. But
so by the time we get there, who knows?
They have, like, other intelligent life on there at that point.
Yeah, and it might not even be habitable when we get there.
Yeah, they might have ruined it already.
Or even just if the calculations were mismatched and the star expanded or something, And then they get there and it's like, well, shoot, now what? Hopefully they account for those potential outcomes before they were to
I would certainly
make
so.
Yeah. Because that would be a concern. Because also, even like the moon, we don't even see the moon isn't the moon even? I guess I don't know how far of a distance.
Well, I mean, the moon's pretty close. But
so maybe we see it like a day, like not a day, but like an hour behind what it is actually. Or maybe we see it in real time. I guess I don't know how far the distance has to be before it starts to distort. Like how long? Because I don't know how far the moon is from Earth, I guess.
So the moon is 238,900 miles from the Earth, exactly. Or at least that's what Google says.
And how many miles can we see in a day? How far can we see in a day before it starts to become the day previous is light, if that makes sense?
How many miles can the human eye see?
Well, more so with like our telescopes.
Okay.
Because like, how when you look at these universes, you're seeing the past. What is
so the time for light to reach us from the moon is 1 1/3 second.
Oh, okay. So it is a second behind.
Pretty close, yeah.
Interesting.
And then the sun is 8 minutes.
So it'll be, if the sun explodes just randomly, we won't see it for 8 minutes.
Basically.
Interesting.
Although it'd be expanding as well.
Unless it was just like a freak explosion.
Of just light.
Oh, like you mean it would be slowly like coming towards us, reaching out towards us? But we wouldn't see it.
I guess so we wouldn't see it. It would still take time before it reached us, but like I would think we would start to see it before it happened. Eventually. Just not right as it happened, maybe.
I guess it would depend on how fast it was traveling and how far we are from the sun, and then time.
That's true.
You'd have to factor. It'd be like an equation.
Well, I mean, that's how science goes.
Yeah. Oh. And space is just so pretty too. Like.
Yeah.
I guess it's mainly pretty because of our eyeballs, all the cones and rods we have to see the light. Yeah.
It's a particle and a wave, I think.
Light?
Yeah, isn't it a particle and a wave?
Maybe.
Or how is that?
I think it can act as a particle or a wave, depending on if it's being observed. I thought that's what it was. Maybe. I don't know. I don't remember.
Yeah, because the particle is a photon. That's right. And the flow of photons is a wave. I see. Okay.
So it like travels on a wave, but when it reaches us, it's a
particle, I think.
I mean, that makes sense. Kind
and
of
a wave, though. It's a wave of particles, is what it sounds like.
Oh, yeah. I guess that makes sense. Yeah. I guess that makes sense, too.
Yeah, that's interesting. Because the wave has different, I think, frequencies. Is that what they're called? It's been a while since I've taken physics.
Like the different light colors? Is that what you're talking about? Or
yeah, like, and the,
like
not
red,
just
orange,
the colors, but also like radio. What's it called? Like electromagnetic, or wait, what am I thinking of? I gotta.
I'm not sure. Like, what are you trying to? Are you talking about light? Just light?
Yeah, I'm just talking about light in general. Like, all light would be like that. And they all have different frequencies. Yeah. And then wavelengths.
Yeah, I like you can view light in different wavelengths. So they all have those wavelengths, I guess, yeah. Like you can view stars' light in infrared or ultraviolet or R. Is that what you're talking about?
I mean, yeah, but you can't view all light, though. You can really only view color light.
Well, us, but telescopes can.
Oh, telescopes. Yeah.
Yeah, not us.
About people. I'm sorry.
No. I don't. That'd be information overload, I feel like, if we could see.
That would be a lot.
Unless we could, like, blink our eyes and then it would switch.
Unless it was.
To...
Yeah, or maybe we didn't, like, necessarily see it in the same way as we see color. Then you'd be able to tell it apart.
Yeah.
And, like, maybe you could just choose, you know? That would be cool.
I think it'd have to have some sort of filter system, though. Because otherwise it, like...
Yeah.
It would just be too much information.
Right, you wouldn't see it all at once, I don't think.
Okay. Because then we couldn't function in reality. Like, in our 3D reality, it'd be too much, like, coming at us, you know? And we'd see too much.
3 dimensions. And we're just used to seeing things the way we see them.
Yeah, I mean, I guess, yeah.
And, like, that's just what we... Yeah, it's just the way we're programmed.
Yeah, it's just the way we evolved. Because we didn't... we didn't need to see X-rays, you know, to function in this planetary world.
Yeah.
Because it wouldn't... I mean, back then, when we were evolving, it wouldn't have served any purpose. I mean, maybe today you could argue that a doctor would be nice to have X-ray vision, because then they could just... Instead of sending you to get X-rays, they could be like, okay, let me blink my eyes here and I'm going to take a look at your arm, you know? So there is potential useful benefit. I mean, although then doctors would have X-ray vision.
Created technology for that?
No, if we had evolved.
Oh, if we evolved to that, okay.
Yeah, like if in the past, per evolution, if developing sensors that could detect X-ray would have been useful, then I think we would have evolved with those. Like, I just think as we were evolving, it wasn't useful. Like, it didn't serve a purpose for our species to adapt and set like a organ that could detect that. You know what I'm saying?
Yeah, it just wasn't necessary for survival.
Yes.
Yeah.
Yes. But we could develop technology
Yeah.
that could potentially add like a functionality of that.
Like glasses or something. That would like convert each, different type of light into like some kind of color or something. Or not like a color, but like, like it would
like a color.
Like kind of like how when you walk into a room and it looks like you have UV light, but it's like purple.
Oh, yeah. Or like even when you're looking at like the images of space from like the X-ray telescopes or the ultraviolet telescopes, like you still see color. It's just different. But I guess, I don't know, like a microwave telescope. What does a star look like? Microwaves.
Mm-hmm.
I don't even know if it would look like anything, It would just be, I don't know.
Yeah. It'd be interesting.
So what other waves are there? Microwaves and gamma?
Infrared.
Infrared.
I think gamma, yeah. I just had it pulled up. Let me pull it back up.
And X-rays.
So yeah, there's gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio.
Oh yeah, radio wave too.
Yes.
I feel like that would have been on our ears. Right? Yeah. You think?
Well, I think I would imagine, and this is just a guess, but like they probably, when they invented the radio, I would imagine that they just chose to send the sound waves through radio waves because they're the biggest wavelength and the lowest frequency. Although, it can change frequency and wavelength, but
yeah. I guess that I don't know.
That would be my guess, though. But I don't know.
I'm not very versed on those waves, but we can go over them sometime.
Yeah,
we should.
Sure.
Waves.
We can talk about light one day. That would be a really cool topic.
Yeah.
Because there's a speed of light too. Like, why is the speed of light the fastest speed in the universe that we can go? Like, why is that the limit?
That's a question you're posing for that episode?
Right, for that episode.
Okay. So I was like, I don't know.
I was just asking into the abyss. I didn't expect you to have an answer.
Because I said so.
Yes.
Because that's what your parents told you, so you have to believe it.
Yes. Exactly. The sun isn't real. It's made up by the Illuminati.
Pretty much. Just like everything, like all of reality is.
Yes.
Like carbon, what is that? Nothing.
Doesn't exist.
Nope. Why would you think it does?
Exactly.
Okay.
Okay.
Do you have anything else to add before we close off this series episode for the day?
Yes, we're good.
Well, if you guys have any topic ideas that you would like us to discuss in future episodes, just leave a comment below letting us know.
You can find us on Facebook, YouTube, Instagram, Twitter, and TikTok. We occasionally do Twitch live streams.
And don't forget to like, follow, or subscribe, and turn on notifications so that you know when we do. Otherwise, we will see everyone next time.